In 1905, Einstein, with his theory of relativity, had shaken conventional concepts of time and space. To an observer, if an object is moving at almost the speed of light, namely 186,000 miles per second, time will appear to be passing more slowly. In 1913, Bohr had given a bold explanation of the relationship between light and matter. The atom, the smallest unit of all matter, emits and absorbs energy in the course of so-called quantum jumps. The quantum jump was a transition between two states which physics was quite incapable of describing. It was the development of modern atomic physics, quantum mechanics, in the 1920s that was to separate the two physicists. The Niels Bohr Institute in Copenhagen became one of the most influential centers of physics. Physicists came from all over the world to work here with Bohr. They were faced with conditions in the atomic world that were quite incompatible with traditional thinking. For centuries, light had been described as waves, but in 1905 Einstein had demonstrated that it also had a particle nature. These light particles were called light quanta, or photons. The same thing applied to the atom, whose components were first regarded as being solid particles of matter. But other experiments demonstrated that they could just as well be regarded as waves. How were light and matter to be understood in the face of such contradictory descriptions? In 1927, Niels Bohr compounded the experiences of physicists into an explanation of these problems. To observe atomic particles, you have to use measuring instruments. And this will have its consequences, because observation will inevitably disturb the atomic particle. What we see in reality, Bohr called a phenomenon resulting from an interaction between the measuring apparatus and the atomic particle. When in one experiment the components of the atom behave as particles of matter, and in another as waves, this is due to interactions with different kinds of measuring apparatus. Niels Bohr called this condition for our perception complementarity. Although the particle and the wave cannot be united in an overall picture, we must still accept them as equally necessary for the best possible description. The atom, as it is, free and isolated, thus lies quite beyond our capacity for perception.
Bohr developed a view in which he essentially would say that reality was unknown or unknowable, or even had no meaning in reality by itself. Reality was, except on the large-scale level of ordinary experience, as atomic reality had no meaning. All that we had were phenomena produced in an experiment, and that and the quantum theory deals with the interrelationship of all these phenomena.
Bohr was not a professional philosopher. How much of traditional philosophers he read, one doesn't know. But he was an extremely intelligent man, and he must have thought through some of the issues that professional philosophers had thought through very deeply. And certainly one of the issues that he had thought through considerably, with some help, I think, from reading, was the Kantian issue of the status of a thing in itself. The thing as it really is, quite apart from any human perception of it. Bohr, like Kant, was very suspicious that one can say anything significant, intelligent, controllable about the thing in itself. He once said that physics or science in general is not about nature, it's about nature exposed to our observation. And that is very Kantian.
This was more than Einstein could accept. It might be necessary for the time being to describe the atom by the contradictory terms particle and wave, but eventually a complete understanding of the atomic world must be possible. He was always reminded of the harmony that reveals itself in all being. To the very end, he worked on describing the universe in a unified theory. He once compared it to solving a well-designed crossword puzzle. You may propose any word as the solution, but there is only one word which really solves the puzzle in all its forms. It is an outcome of faith that nature, as she is perceptible to our five senses, takes the character of such a well-formulated puzzle. The successes reaped up to now by science do, it is true, give a certain encouragement for this faith. Einstein disapproved of Bohr's view that our knowledge of reality in physics consists of phenomena resulting from interactions with a measuring instrument. Einstein wanted to understand physical reality as it exists independently of our observation. He made his point by telling Bohr that God does not play dice. Bohr retorted that Einstein should stop telling God what to do.
In Einstein's talk that he gave before my relativity seminar, the last talk that he ever gave in his life, in it he spoke about relativity and what it meant to him, how he had come to it. But then he went on to speak of the quantum physics. And there he spoke of his discomfort with the idea that the choice by the observer or the observing equipment has anything to do with the matter. He put it this way as he paced up and down before the black table. If a person, such as a mouse, looks at the universe, does that change the state of the universe? His vivid way to make it seem preposterous.
In 1935, Einstein presented Bohr with a final challenge. This thought experiment was only ultimately clarified many years later by the French physicist Alain Aspect. In an article which he wrote together with two other physicists, Podolsky and Rosen, in the Physical Review, Einstein posed the question, does quantum mechanics provide a complete description of physical reality? Einstein wanted to demonstrate that it was possible to perceive a part of physical reality without its being disturbed by the measuring apparatus. The experiment allowed two particles with common properties to be emitted from the same source. It should then be possible, by measuring one of these particles, to obtain knowledge about the other particle without disturbing this other particle in any way. But the real purpose of the thought experiment was to demonstrate that Bohr's atomic physics contained certain absurdities. In this same example, the consequence of quantum mechanics would be that a measurement of one particle would exercise an influence on the other. In fact, only then would the properties of the two particles be determined at all. In principle, the other particle could cross enormous distances in time and space. Bohr's atomic physics therefore implied a paradox. It conflicted entirely with Einstein's picture of the world. No event could create an effect simultaneously somewhere else in space. In Einstein's view, the different parts of the universe were only connected with each other through effects or signals that could not be transmitted faster than the speed of light, and whose origins could always be traced back to a cause in an individual part. Einstein claimed that all events have a local cause.
Local causality is the idea that what we do here in this region of space has no immediate effects in a distant region of space. In fact, it has no effects until a lapse of time which is limited by the velocity of light. Now, this was an important principle in Einstein's relativity. There's one to which he was strongly attached, and it is one which is not present in quantum mechanics, because quantum mechanics doesn't give you this analysis of the world into different space-time regions. The whole thing is treated as a unified thing, and Bohr insisted very strongly on the indivisible nature of quantum phenomena. If two particles had interacted and separated, they were still one system, and it was wrong from Bohr's point of view to try to think of how to divide it up into something happening in this space-time region and something happening in that space-time region.
At the Institute in Copenhagen, Einstein's article came as a great surprise to Bohr. The physicist Leon Rosenfeld was working with Bohr at the time. As soon as Bohr had heard my report of Einstein's argument, everything else was abandoned. We had to clear up such a misunderstanding at once. In great excitement, Bohr immediately started dictating to me the outline of such a reply. Very soon, however, he became hesitant. No, this won't do. We must try all over again. We must make it quite clear. So it went on for a while with growing wonder at the unexpected subtlety of the argument. Eventually he broke off with the familiar remark that he must sleep on it. The next morning he at once took up the dictation again, and I was struck by the change in the tone of the sentences. There was no trace in them of the previous day's sharp expressions of dissent. As I pointed out to him that he seemed to take a milder view of the case, he smiled. That's a sign, he said, that we are beginning to understand the problem. In his reply, Bohr emphasized that our ideas and concepts are rooted in our everyday experience. We are therefore incapable of forming a picture of the atomic world. Strangely enough, Bohr refrained from refuting the paradoxical consequences of quantum mechanics as described by Einstein. He believed that the two particles should be understood as a unified system. We have to do with a wholeness that is completely foreign to classical physics, he said.
Bohr once said that clarity and truth are incompatible variables or complementary variables, and perhaps that Bohr's answer is true, but I am sure that it is not clear. Well, roughly speaking, as far as I understand it, Bohr said that you cannot consider separately the various pieces of an experiment. In Einstein, Podolsky, and Rosen reasoning, they were considering on one hand the system on which bears the measurements, and on the other hand the measuring apparatus. And Bohr said you have to consider everything as a whole, the system that is measured and the system that you measured. Everything is a whole, and if you are not allowed to consider different parts in the experiment, then the Einstein reasoning no longer holds.
There is a famous sentence something like that: although there is no influence of the one experiment on the other, there is a change in the very conditions for the possibilities of knowledge. There is a very well-turned sentence which I believe Bohr took a great deal of trouble in formulating, and whose meaning is just absolutely obscure to me. So what I get out of Bohr's reply, and certainly what Einstein got out of Bohr's reply, was simply the insistence that we have no right to a picture of the atomic world.
It was John Bell who in 1965 derived a theorem which proved that Einstein's thought experiment could be carried out in practice. John Bell became the judge of the controversy.
At the time of Einstein and Bohr, it was just a theoretical discussion. You could endorse either Einstein's position or Bohr's position, and it was just a matter of taste. And then there was the great discovery by John Bell in 1965 that it is not only a matter of taste, because according to the position that you have, at a certain point, you have predictions which are not the same. If you follow Einstein, you have a certain type of predictions, that is to say, you have results in agreement with what is called Bell's inequalities. And if you follow Bohr's position, you have another type of prediction which are in contradiction, in opposition with Bell's inequalities. And this was a good reason for doing the experiment.
In 1982, in Paris, Einstein's thought experiment was put into practice. Aspect's experiment involved the polarization of photons. Polarization means that light oscillates in specific planes. A polarization filter will only permit light to pass if it oscillates in a specific plane. In Aspect's experiment, lasers irradiate the element calcium. This causes two photons to be emitted from the same calcium atom simultaneously. Measuring instruments on both sides register the photons. In order to determine the polarizations, polarization filters are inserted. Sometimes the photons pass through. At other times, they are stopped by the polarization filters. The measuring instruments register the photons that pass through. The polarization filters can be turned so that it is possible to register photons of other polarization directions. Aspect compared the polarizations of the two photons and observed a correlation. If the polarization filters were set identically, both photons would always either pass through or be stopped. How could this correlation between the two photons be explained? One possibility was that the polarizations of the two photons might be predetermined from the very moment of emission. This would be entirely in the spirit of Einstein.
A reasonable picture in the mind of Einstein was to admit that at the very beginning the two particles have something in common. They bring with them a common property until the last moment. And at the last moment, when you make the measurement, the result of the measurement is due to this property. So you have a property at the beginning, then each particle brings a property, and then the result of the measurement depends on the property, and there is nothing spooky in this picture. This was a picture by Einstein.
In order to find out whether the polarizations of the two photons could be predetermined, the respective settings of the polarization filters would have to be different. Then one might expect a certain limit to the number of pairs of photons that ought to pass through. This limit was known as Bell's inequality. Aspect performed measurements of many thousands of pairs of photons. A counter connected to the measuring instruments recorded when both photons passed through. The setting of the polarization filters was varied in many directions. However, the results of the measurements showed that it was impossible for the photons to have predetermined polarizations at the moment of emission.
If you believe that the property belongs to the photon from the beginning, from the emission to the source, then the result of measurements must obey to a certain inequality that you call Bell's inequalities. And we have found experimental results violating Bell's inequalities. So we are compelled to reject the idea that the polarization of the photon was already existing just after the emission.
The experiment thus pointed to the peculiar fact that the photons chose a common polarization at some moment or other after their emission from the calcium atom. Could it be conceivable that an unknown signal would have time to inform the photons about the setting of the polarization filters? Einstein's theory of relativity insists that no signal can be transmitted faster than the speed of light, namely 186,000 miles per second. Aspect was obliged to improve his experiment.
You have to change something on this side fast enough in order to change it before any information has been transmitted to the other side of the experiment. There are 12 meters between both ends of the experiment. It takes 40 nanoseconds for the light to travel from this end to the other end. If I change something in less than 40 nanoseconds, then what I do here will not be known by the apparatus on the other side.
On both sides, Aspect now placed two polarization filters with different polarization directions. And in between them, a specially developed optical switch. The optical switch now sends the photon out to one of the two polarization filters. It cannot know to which. The switch changes direction in a millionth of a second. Everything now took place so fast that even an unknown signal traveling at the speed of light would not have time to inform the other photon.
And when you switch here, this optical switch, from the up to the down direction, everything is equivalent to a single polarizer that you turn from the first direction to the second direction. And all this system is equivalent to a single polarizer that you switch very fast within a few nanoseconds from one direction to another direction. This was a trick used for the experiment.
Once again, Aspect made measurements of thousands of pairs of photons. And he was still able to observe a correlation between the two photons. Either both photons would pass through, or they would both be stopped. This decisive version of the experiment established the paradoxical fact that the photons did not decide on the same polarization until the actual moment of measurement, when they're 12 meters apart, a distance that could have been infinitely greater.
We have found results in perfect agreement with the quantum mechanical predictions. There is absolutely no deviation, and quantum mechanics predicts that this correlation will not change when you go very far apart, even if you go to cosmological distances.
The conclusion of the experiment supported Niels Bohr's contention that the properties of the two particles are not determined until the moment of measurement. This was what Einstein in 1935 found absurd and described as spooky actions at a distance.